Welcome to EDU World Space.
The Bohr model of the hydrogen atom is basically a semi-classical model of an electron in orbit around the proton. The one part that is non-classical is to take the electron's orbit, assuming that the electron has a wavelength given by p is equal to Planck's constant over lambda, and to try to quantize the circumference of the orbit as an integer number of wavelengths. Okay, so the orbit is quantized according to 2 pi times its radius is equal to some integer times wavelength, where the integer is 1, 2, etc. And the reason this was done is by realizing without that integer relationship, the electron's wave function, whatever that may be, would actually interfere with itself and cause the electron to sort of disappear in orbit or cancel itself. And so this quantized relationship made some sense. Okay, so let's take the circumference being quantized in units of lambda, and let's take angular momentum, L. Angular momentum is a product of mass, and here we're going to use the reduced mass with the understanding that that electron is moving around a massive nucleus, but it does have a little bit of mass and may wiggle a little bit. So that mu is almost the mass of the electron. And let's put in for the quantized radius, and let's use the de Broglie wavelength idea. So by the time Bohr was coming up with his model, we had this understanding of the de Broglie wavelength. So in the parentheses first is h over lambda. That's basically the product of mass times velocity or momentum. And r, if we look at our quantized circumference, is n lambda over 2 pi. So we'll put that in there, n lambda over 2 pi. And you can see what happens is the wavelength cancels top and bottom, and we are left with the angular momentum being n h over 2 pi. And to make life a little bit easier, this gets confusing, but there is a shortcut notation for h over 2 pi as h bar.